An insulated box, with a wall down the middle. Air on the left. On the right, nothing at all, a vacuum. Now pull the wall away. The gas floods the box, and fills every last corner of it. But look at what did not happen. Nothing crossed those insulated walls, no heat went in. And it pushed out into empty space. There was nothing over there to push against, so no work came out either. So energy-wise, nothing happened at all. The gas still has exactly the energy it started with, and exactly the temperature it started with. Now run the film backwards. You already know this one is wrong. Nobody has ever seen air pile itself back into half a room and leave a vacuum behind. Not once. So we are left with two questions. Why never backwards? And since something quite clearly changed, how much? One single word answers both of them. Take the first question, and forget joules for a minute. Just count. One molecule has two places it can be, left or right. Two ways. Pulling that wall doubled its choices, twice the room, twice the ways. That bar down there is our real box-keeping score. How many molecules are on the left, right now? Watch it wobble, and watch it never go all the way over. Now 2 molecules. 4 ways. And only one of those 4 is tidy, with both of them back on the left. 3 molecules, 8 ways. Still only one tidy one. And every extra molecule doubles it again. 16 ways. Then 64. Then 256. For n molecules, 2 to the n. And if you tripled the room instead of doubling it, it would be 3 to the n. So going home isn't illegal. It is outnumbered. But just how outnumbered? Write 2 to the n out in full, for 1 kilogram of air. The number itself would have more than 10 to the 24 digits. One tidy arrangement, hidden somewhere inside that. A landslide, not a ban. Now one catch. Counts multiply, but a property really ought to add. So take the logarithm, ln, the natural log. The one thing you need from it is this. What's the exponent? It walks out front. In other words, times became plus. N separate copies of log 2, simply added up. And that is this famous label. W counts the ways. And Kb turns a bare count into joules per Kelvin. It is Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin. One piece of bookkeeping before we go on. Capital S is the whole box, in joules per Kelvin. Small s is per kilogram, joules per kilogram per Kelvin. Small s is the one we are going to compute. And hold on to that log 2. We will meet it again. Now the engineer's half of the story, an actual number. A nudge of entropy is the heat you put in, divided by the temperature you put it in at. So let a little heat in, and watch. The jiggling speeds up. And the temperature climbs. Now read the small print, because it is doing real work. Reversible means a path so gentle that you could run it backwards, and leave no trace at all. Like this, forwards, and back again. Now aim that definition at our exploding box. The walls are insulated, so the heat never gets in at all. So the top of the fraction is 0. And 0, over 300, is 0. So, nothing changed? But the counting said the ways exploded. Both of those cannot possibly be true. And they are not. We aimed it at the wrong path. That flood was the most irreversible thing in the room. There is no way on earth to run it backwards. Reversible was never decoration. It was a condition, and this path fails it. Here is the rescue, and it is the whole idea of this video. Entropy is a property of the gas, exactly like its temperature or its pressure. And this state just means the gas's condition right now, what a set of gauges would read. Its temperature. Its pressure. And this little v, the room that 1 kilogram of it takes up. Its volume, per kilogram. Tell me the state, and the entropy is already decided. For our box, both end states sit at the very same temperature, 300 Kelvin, because the energy never changed. The two dots are level. The whole story is the gap across. So what about the real explosion in between? You cannot draw it. Halfway through, one corner of the gas is racing and another has barely started. It doesn't have a single temperature to plot. So don't draw it. Take any reversible road you like between the same two dots. Road 1, pull a piston out slowly, holding the gas at 300 Kelvin the whole way. Watch the box grow, and watch the meter underneath measure the entropy out as we go. There. Road 1 lands on state 2. And notice I am deliberately not putting a number on that meter yet. Now take a completely different road. Road 2 also expands with no heat. But this time the gas leans on a real piston and shoves it out. Pushing costs energy, and it is paid straight out of the gas's own pocket, so it cools down to 227.4 Kelvin, at exactly twice the volume it started with, the very same V2 that Road 1 reached. Then we clamp the volume there, and warm it back up to 300. And it lands on state 2 as well. Same two dots. And the meter counted out exactly the same amount, both times. That is what it means to call entropy a state variable. And it is the only reason anyone can put a number on an explosion nobody could follow. Hold on, something ought to be bothering you. Both of these had no heat, and they did opposite things to the temperature. One stayed at 300 Kelvin. The other lost 73 degrees. So what is the difference? Work. On the left there is nothing there to push against, so no work is done at all, the energy can't change, so neither can the temperature. On the right the gas shoves a real piston, and that work is paid out of its own energy. Paying makes it cold. Same no heat, different work. So let's walk a reversible road and collect the formula. Start from the definition, and clear the fraction, multiply both sides by t. But first, let's earn one piece of the first law. Everybody writes the work as P/dV. Why? The gas presses on the piston face. Pressure is force spread over an area, so the force is P times A, where A is the area of that face. Now let the piston slide out a tiny distance, dx. Work is force times distance, so the work is PA times dx. But look at that shaded sliver the piston swept out. Area times length, A times dx, is the extra volume the gas just gained. That is dV. So the work is simply P/dV. So here is the first law from last time, on its own line. For one tiny reversible step, the heat you put in splits in two. Part of it raises the gas's internal energy, that is dA. And the rest walks out as work, which we have just shown is P/dV. Now the substitution on its own, so you see exactly one thing change. That right-hand side is delta Q reversible, so drop the first law straight into it. Now two perfect gas facts finish it. 1. The internal energy of a perfect gas depends on nothing but its temperature, so dA is CV times dt. And CV is the joules it takes to warm 1 kilogram by 1 Kelvin at fixed volume. For air, that number is 717.5. Hold on to it, we are going to need it. 2. The ideal gas law. Pressure is RT over V. R is air's own gas constant, 287 joules per kilogram per Kelvin. Every gas has its own R, this one is air's. Swap it in for P. Now divide every single term by T. And look hard at that last term. There is a T sitting upstairs, and a T sitting downstairs. And AT over AT is 1. Strike them both out. What is left of that term is our dV over V. Nothing was waved away, the T really did cancel, and you watched it go. Last move, add up every one of those nudges, from state 1 all the way to state 2. But notice what we just did. We pulled CV and R out in front of the integrals, and we are only allowed that if they are constant. That is a stronger promise than a perfect gas. It is called calorically perfect, the specific heats don't drift with temperature. For air below about 1000 Kelvin, it is a good deal. Now look at the two integrals, they have exactly the same shape. 1 over something, times d of that same something. And we are about to lean on one fact, so let's not just assert it. This is the curve 1 over x. Shade the area underneath it, from 1 out to 2. That shaded patch measures 0.693. And that is the natural log of 2. So that is all a log is doing in here, it is an area under 1 over x. And remember that 693. It is coming back. So each of those integrals becomes a log, evaluated at the two ends. That square bracket, with a 1 and a 2 on it, just means this: put the top value in, then subtract the bottom one. And a log minus a log is the log of a ratio. Watch them fold together. And there it is. In other words, the change in entropy is CV times the log of the temperature ratio, plus A times the log of the volume ratio. Now read what is actually in it. State 2, and state 1. Not one single word about the road. Now feed our exploding box into it. Its energy never changed, and for a perfect gas, energy is temperature. So T2 equals T1. The ratio is 1. The log of 1 is 0. And that whole first term vanishes. What is left is the volume term alone, and the gas got exactly twice the room. So delta S is A times the log of 2, with the air constant per kilogram, 287. And the log of 2 is 0.693, the very number we measured off that curve a minute ago. 287 times that is 199 joules per kilogram per Kelvin. There it is, the number, at last. Positive, exactly as the counting promised, for a process nobody could follow. But hold on. We got that by walking road 1, where the temperature never moved, so every joule of it came out of the volume term. Does road 2 really give the same answer? Leg 1 was reversible and had no heat, and no heat means no entropy nudge. So that leg gives exactly 0. That is why it drops straight down. Which leaves leg 2, the reheat, from 227.4 back up to 300, with the volume clamped. Clamped means V2 equals V1. So this time it is the volume term whose log is 1, and it disappears. So every joule now comes from the temperature term. 300 divided by 227.4 is 1.319. The natural log of 1.319 is 0.277. And CV for air is 717.5. So clear the meter and let road 2 fill it from scratch. 717.5 times 0.277 is 199. There is the whole argument in arithmetic. Different symbols, different numbers, different physics, one road paid in volume, the other paid in temperature. 199, both times. They don't just agree in the picture, they agree in the arithmetic. Now let's cash the counting in. The ways went up by 2 to the n, so the entropy of the whole box went up by kb times the log of 2 to the n. And the exponent walks out front, so that is n times kb times log 2. And here is the joint between the two halves of this video. That box down there holds 1 kilogram of air. How many molecules is that? About 2 times 10 to the 25th. Now multiply that many by Kb, 1.38 times 10 to the minus 23 joules per Kelvin. And out falls 287. Which is R? The gas constant per kilogram was never anything but Boltzmann's constant, counted 1 kilogram at a time. So delta S is A times the log of 2. And that 2, right there, is this 2, the 2 places one single molecule could be. So entropy was never a story about the journey. 2 end states in, 1 number out, which is how we put a number on an explosion we could not even draw. And that gas is not going home. Not forbidden. Outvoted, 2 to the n, to 1. Next time we set delta S to 0, we hold the entropy perfectly still and outfall the isentropic relations.